Where are we going? Let's check the GPS. Welcome to this really special episode of the Engineering Word of the Day podcast. I'm Pius, your host, and my guest is the incredible electrical engineer Hugo Fruehauf, who's helping explain today's engineering word of the day, GPS. Of course, we all know GPS as that thing hooked up invisibly to our cars and phones to tell us where we are, and it's really an acronym, not just a simple word. GPS stands for Global Positioning System. And why is Hugo Fruehauf the perfect person to talk about what GPS is? Well, he helped invent it.
Hello.
Hello, is this Mr. Hugo Fruehauf?
It is.
Hi, this is Pius Wong from the Engineering. Hugo Fruehauf was one of 4 American engineers who won the prestigious Queen Elizabeth Prize for Engineering for 2019 for the invention of GPS. He was honored last December in the UK, along with other leading inventors, Dr. Bradford Parkinson, Richard Schwartz, and the late Professor James Spilker. I spoke with Hugo over the phone to learn more about what GPS really is and how he got to take part in its invention. Yeah, I'm just wondering, how does it feel to be recognized for this pretty important technology of GPS?
Well, the whole thing with going to Buckingham Palace and receiving an award, you feel like you're dreaming. You don't want to wake up. So that's kind of where I react. But this kind of conversations were bound to happen sooner or later. I was part of it right from the beginning, both on the satellite design and the clocks. And so we actually got a 40-year-old award, and you kind of wonder, how's it possible? 40 years to get an award. Well, we did a good job 40 years ago, and the thing still works like a charm.
Yeah, so let's talk about the technology, actually. As an engineer, I really am interested. First of all, what is GPS? What did you work on 40 years ago?
Probably the best way the way I look at it is I was a World War II kid in Germany, so I know all about carpet bombing, and the root of GPS certainly contained that element when the military people start thinking about the next kind of warfare, and we certainly didn't think it was going to be, carpet bombing and having 2 sides of battle. It's going to be not strategic, but tactical warfare. And the only way to do that right is to reduce collateral damage. Mm-hmm. So the whole idea of having a military system that could navigate our military and target weapons was, quite well and alive in the 60s. Not in the 60s, in the 50s and mid-60s. So to make a point here then, is the government always had in mind to not only have a military capability, but also to provide a signal for the world, so to speak. And so the signals that you can't receive that are encrypted and all kinds of things like that are in the military. And what you enjoy today is, as much as 5, maybe sometimes mostly 10 feet or less accuracy, so you know which lane you're in. And that's a commercial unencrypted signal, which was guaranteed by President Reagan back in the early 80s to give to the world, and President Clinton in the year 2000, who then made that commercial signal fully available to give to the world, has already, some people say, generated $1.5 trillion since the year 2000. For the commercial sector.
Wow.
So in that light, then, I look at both. I'm obviously more sensitive about the collateral damage than anybody else, since I was a kid during the war. Yeah. But it's a dream come true. There's a lot of good people that worked on this, and unfortunately, not everybody can get an award. But we finally got it going, made it work, and that's what you got today.
Yeah, you really clarify how this was a huge project, and I know that there were, of course, many people who worked on it, and 3 of your colleagues got the award with you, but I'm sure there are many other names that you could associate with it. Can you talk about at least your section of the project that you worked on? I understand that you helped develop the atomic clock that goes with GPS.
Yes, I started working on GPS. What the government does essentially is when it begins to do some really big things, they like to use the term commercial and military coexistence. What that means is the military spends a ton of money on something, and the commercial element of it, like GPS signal that you're aware of, then pays for all the expenses, 10 times over, and that's called commercial and military coexistence, meaning that the military is completely isolated, undisturbed by what you do with the commercial side, and the commercial side is, completely separated from the military. And so that's a wonderful way to build stuff. You build stuff that has a commercial content, and as a result, you have very good contracting. And so the government then, in that light, puts out requests for proposals, and then people like RCA at that time, Philco Ford, Grumman, and Rockwell International, you kind of bid on these things. You put together a team of experts in every area, payload, orbital mechanics, power, signal structure, and all this kind of stuff. Mm-hmm. And so my boss helped me put together a team back in 1973, and we picked the best people we had at that time, and it began to utilize a lot of the stuff that was already been tested by the government, and I was assigned as the chief engineer on the satellite, and that was the beginning part of, for me, was in the beginning of 1973. The clock part of it, an atomic clock is not radioactive. No, atomic clock simply means that the element that makes the time work is atoms, where your wristwatch is a quartz disk, and your grandfather clock was a long pendulum. So, essentially look at it that way. Mm-hmm. The atomic clock is the ultimate accurate pendulum, so to speak. So the thing that was interesting for me is that, Brad Parkinson, who is really the father of GPS, struggled very hard to get this program going. And as part of that process, he was going to be using 21 Atlas F ICBMs that the government wasn't going to use. It's an Atlas booster. It has a throw weight of about 1,450 pounds. The reason I'm telling you all this is when you get all done, the satellite that we originally built weighed only 850 pounds. Mm. And then on top of that, you had a kick motor that goes from, like a lower perigee at the lower side of the orbit to apogee of 12,000 miles roughly. Had to have another 500-pound kick motor. So I was struggling with the weight of the satellite. It just wasn't enough booster. Today, the satellites can do anything they want. They just have SpaceX use a different booster. Mm-hmm. So it was a different problem. So long story short then, the clocks that clock we needed was something that you sit in the lab, that's been in the laboratory since the 40s and 50s. In the 40s, there was a refrigerator-size atomic clock, and for laboratories in the 50s and 60s, then they became, two microwaves, and we couldn't use any of that technology. First of all, the radiation is so harsh that my hardening guy, the engineer that did all the radioactive hardening stuff, said that if you were sitting on the satellite, you'd be dead in less than 10 seconds. So. Yeah. Give you some idea of the cruel environment we're in. So the clock then, essentially what was available was just not going to do it. We needed something a lot smaller. Well, it happened to be that a bunch of guys from Germany, Ernst Jeschert and Gerhard Hübner, built a small little device, and basically really had no market at the time. This is back in the late 60s. Mm-hmm. They came up with a way of making an atomic clock, 4 by 4 by 4 inches instead of 2 microwaves. It was fantastic, but in Germany they just didn't see any need for it. He found a customer that was going to use a small atomic clock for an Omega navigation set back in 1969, and there was a system, Omega, that was ground-based, would ground long cables, and you radiate from the ground with large towers. But if you had an atomic clock in there small enough, in that briefcase-sized unit that we were talking about, you could then fly places without one of the signals. And so the idea was to use an atomic oscillator, and the couple I just mentioned, one of the founders came to the United States and set up a small shop right near Rockwell, unbeknownst to me at the time, and selling this 4x4 by 5-inch atomic clock, very good, to this customer in Costa Mesa, California. My frustration of not being able to get anywhere was just came out of it got solved out of the blue when I was introduced by chance to this Gerhard Gernst-Jeschert, who had moved to a small company with a couple of 3 people.
Wow.
He had this small atomic clock, and I thought to myself, my God, this can't be right. After 8 hours, I was dizzy. I thought I was dreaming.
Like it was fake or something.
Yeah. So long story short then, in the next year or so, we worked together, and I have some reasonable knowledge in this area from the laboratory standpoint, and Rockwell then with a teaming agreement with what was at that time called Efratom, which the founders of Ernst Jeschert and Gerhard Hübner, we started. They did some physics, and we built the entire system, electronics and hardening and It was about a year effort, and we were able to get a atomic clock in there that was maybe twice that size. It was about 6 by 5 by 4 or something like that. And that's the story of the atomic clock. As a matter of fact, just a couple of years ago, we turned one of them off that was launched in the 90s. In the 90s, the atomic clocks that we started with in 1978 were still the clock of choice. There was nothing else available. And last year, in January of 18, we turned off one of the longest clocks. It was turned off after 24 years of operation.
Wow.
So that's the story of the clock.
Yeah, thanks. And just to be clear, this subsystem that you've developed, this atomic clock, besides just being small and up there, like it's a critical piece of equipment, right? Without it, what would happen to the GPS system?
Well, you have to look at it this way. GPS is the clock, and the clock is GPS. Without the clock, then you can shut down all the Air Force bases. You can shut down everything. You're not going to. The clock is the central number one key figure, because you got to have something so accurate to a nanosecond to be able to measure the speed of light. Mm-hmm. The speed of light travels about 3 feet in 1/billionth of a second. So you can imagine that if you have a clock that's 2 billionths is 6 feet, and a small number ends up being 100 to 200 foot error. So the clock has to be better than a billionth of a second to measure the speed of light, because that's how the signal comes from the satellite to your receiver, and roughly it travels at the speed of light, like all other FM radio stations and everything else.
And so today the GPS system is super accurate. I forget how accurate. We can get it within a couple feet. Is that correct? Yeah,
your cell phone car thing probably does on an average of 5 to 10 feet, I would say, easily. Now, with the GPS being augmented, for instance, we call it augmentation systems, where you have another tower that's measuring GPS with high-performance receivers, and then corrects and so on. You can get down to millimeters. Right now, we're measuring tectonic plates at a couple of millimeters in movement.
So I still have more technical questions. I do want to ask a little bit more about your background, if you don't mind, but just one more technical thing. For the Engineering Word of the Day podcast, I often like to talk about where the words even come from. And I noticed that when I look up GPS, it's not just called Global Positioning System, it's often called the Global Positioning System, because there's only one system. Is that right?
No, that's not right.
Oh, okay.
Probably we were the first, and as I mentioned earlier, position targeting was everything, and then having a commercial element to it.
Okay.
Now, the Russians started a program called GLONASS, and they began to build satellites and have the same kind of orbits and the same kind of thing. The signal structure was not quite good enough in the beginning. However, now their satellites is using CDMA, pseudo-random noise kind of signal that we basically invented as Americans. And so they started a system that became operational about 5 years after us. We were fully operational somewhere in the early 90s. And then Europeans started their own system called Galileo, where, again, it's a basic copycat from us. And then the Chinese Baidu system is now also being developed and probably be operational in a couple of years. And Galileo for Europe will be operational in probably in a year. Now, the question you're thinking of now is, we got one good system, why do we have everybody else do a copy? Well, for the commercial element, all the countries agreed that they would send a signal into the same think of the football field and everybody's got raindrops falling, and the 1,023 bits of GPS is like a raindrop falling in a football field. And every satellite has a different code, and so therefore we agreed that the commercial signal would always be capable of having everybody's satellite navigation system be able to communicate with, and use that same frequency. And the reason I mention that is because we now, if you're in the future, you'll be navigating with, you don't know. The receiver will pick the satellites based on position and how accurate the clocks are between them. And so you could be having one Chinese satellite, two from us, and somebody, a bunch more from Galileo. So that is the good part. And essentially, as we are no longer the only people that would do this. So therefore, everyone is going to be participating, with the military again being separate. Now, why would the other people have a system like GPS? Because GPS, they want to use that for the military. So you see, everyone now wants to be able to do what we do for the military purposes.
And so is GPS and even these competing systems, are they still evolving then? Are they still changing today?
I think the Chinese are doing a great job, and they're basically everybody is finished, ready to go operational. We were operational in the early 80s and fully operational in the early 90s. And as I mentioned earlier, the competing systems are, about to come alive for both the commercial side of it, which I just described, and for their own military purposes. So everybody wants to have their own system, because they don't want anybody to tell them what to do militarily.
So I often talk to younger engineers, either students who are in college right now or people who want to become engineers, and they often have to learn about basic technologies like engines or the computer, that kind of thing. Is there anything you think that young engineers today that they really should just know about GPS?
Well, GPS is its own world, so to speak, because it has software people, the best there is, hardware people, electronic engineering, computer engineering, orbital mechanics, signal structures, tracking and data and control. It has the power system. It has the antenna systems and HPAs, which is different. Solar array structures, which is part of power system. No, it has about 12 or 13 different disciplines, which are very, very specific. So for me, as the chief engineer on the satellite, I was a good systems guy. I knew there's a lot of great people that will turn your telephone into a raindrop size, and that's chip makers. So those guys are a whole different breed. So in general, I would say, for me, electronic engineering has got to be the center of it, because sure, we need mechanical engineers to make the structure and stuff, but the stuff that really makes it operate, the payload, so to speak, payload means the thing for which it's purposed, ends up being very, very, very electronic.
And so that kind of leads into your background. You are an electrical engineer, right? I was wondering what your background was and how you got into engineering.
Well, I was an immigrant back in 53, 54, and I went to school at that time. It was Dry Tech, and it had a program which I loved, and that was 2.5 years at 50 weeks per year school.
Oh, wow.
And at that time, accreditation of DeVry, which is now DeVry University, was questionable. And so I went through the whole program, got that degree, and that is my engineering background, and it's been the best thing that ever happened. And then after 30 years, I ended up getting a presidential and key executive MBA from Pepperdine University. It served me. DeVry served me because of the hands-on capability for, imagine, 50 weeks a year going to school for 2.5 years.
Yeah.
It was just had everybody beat. Once I got a job, I graduated in 1960, and I was hired by Martin Marietta Company, and they were launching weapon systems from the Cape and from Vandenberg Air Force Base in California. So I'm really a rocket guy, and for the Apollo program, I was in charge of the testing as chief test conductor of the second stage of the Saturn V, which was built by Rockwell, the same company I mentioned, built GPS. We had the contract on, that was before the GPS contract. I was just getting off of the Saturn program in 1973 because Apollo 17 didn't launch, and I started immediately at that time at GPS.
You make it sound so easy, like transferring from this one difficult field to rocketry and doing all this stuff. It's kind of inspiring. In fact, the DeVry University that you mentioned, is that the one in Chicago? Like, I'm from Chicago, and I'm wondering if it's that same one.
So on Belmont Avenue,
yes.
It's called DeVry Tech then.
Okay.
Accreditation was questionable, but
right.
It sure worked for me.
No, I understand. My brother lives 2 city blocks away from there, so I was always in the area. But I understand the news about DeVry. But at the same time, like I talk to a lot of people today, teachers and engineers who want more of that hands-on experience that you talk about. So it's kind of interesting that you say that was important for you.
It's everything. When the first thing I started doing is in 1960, being part of the launch team and start building ground support equipment. It was archaic to me, and I put in countdown clocks. Think about what happens. The Saturn V right now, the second stage was over about 450,000 gallons of liquefied hydrogen. I mean, just imagine. And all these things were tested first before they were flown. Von Braun's idea was that you don't fly anything that you can't test first. And so therefore, we were very busy. I was very busy with my team developing ground support equipment that would make it easy for you to count down a vehicle, through all its phases. And then in Mississippi, at that time it was called Mississippi Test Facility, today Stennis Space Center. We had gigantic test stands that were 300 feet tall, and the barges would come in with the vehicles on them, and get put into these test stands, screwed down, and then you make it think it's flying. So you go through the whole process of counting down the vehicle, thinking it's actually going to let off, and it gets lit off and you make it make it feel like it's flying through all its aspects. The reason I mentioned it about Von Braun is because he was bent on testing everything before put pilots on it, and there was never a second during the launch phase that those astronauts could not have been shot off the top of that huge Saturn V rocket, and the parachute would open and they would go into the Cape Canaveral Bay. Never a second were they in danger. Now, why do I say that? Because we killed 14 people, 7 of them on the ground and a few more, and 7 in the... And part of that problem is what I said about Von Braun. How do you test a solid rocket motor on the side of a spacecraft? You can only test the one that like one, but you can't test the one that flies, right? It's like testing a 4th of July rocket going up. You can only test another one that's like it, but not the one you're going to fly.
Right.
That's what kills people. And so, we were very busy. The first generation NASA was fabulous. The second generation, read the accident reports to judge yourself. Now we have a third generation coming along. And yes, I've been in SpaceX facility in Hawthorne twice. And they have brilliant people, a little bit too young for me, a little bit too arrogant, to be honest. So anyway, that was my background. Then as soon as I left Martin Marietta and joined Rockwell, I was privileged to become the chief test conductor at the age of 27.
Wow.
So.
Yeah, I think test engineers in different fields have different reputations, but I think in the media, a lot of people think test engineers just blow things up, but it sounds like you have to be really disciplined to save lives and make things work.
Oh my God, yes. So systems engineering, I was a good circuits guy too, but systems engineering, putting block diagram together and say, do this one, do that one, to reach an end, that's my bag, systems engineering.
Yeah.
So that would be the long answer to your original question.
Okay. No, that's fair. And I had read that not only were you working as an engineer, but you led a lot of people. You worked your way up basically to be chief technology officer for more than one engineering organization. Is that right?
No, actually, it's actually better than that. After I left Rockwell, after we launched the first few satellites in February of 1978, I left Rockwell and became the president of this German company called Effertom, and chief technology officer and president. And I have been on every job I've had. I've been the CEO. So
yeah, wow.
Yeah, I never worked except until 1973. After that, I was CEO of every place until I retired, sort of retired.
That is a lot of engineers' hopes and dreams in a way. How did you make that jump, I guess? I'm sure it wasn't just instant. You worked really hard. So what are some tips, I guess, you could give to engineers in industry to achieving that?
Well, that's an interesting question. I've always just automatically got these jobs. And the reason is two things. One is I believe strongly that CEOs of companies, especially technical companies, ought to be led by somebody that is really, really, really technical. And that's been always my bag. I could lead companies into new products. For example, after I took over the German company in California, we built it up to, about $100 million, close to that a year in, atomic oscillator applications. We had them in tanks. We had them in airplanes. We made them radiation hardened. We made them military hardened. We just, went through the whole process of all the possible applications. And one of the early ones that ended up, being huge success was cell sites. Cell sites. To locate the cell sites and have an atomic oscillator in the cell sites, you never have to send in another maintenance or calibration engineer. Atomic oscillator will keep such accurate time that when you're moving from one cell site to another in your car, you can't be out more than a microsecond of time. Otherwise, you get stuttering or pops and stuff like that. So the atomic oscillator found its in the United States alone, 400,000 units we sold into cell site systems in the 80s.
Wow. And
then in 1997, I joined my boss that I had both for the Apollo program and for GPS. He was the CEO of Alliant Tech Systems in Minneapolis, a spin-off of Honeywell, and I was the president of their defense group. And, went right back into inventing stuff. You have to invent stuff to make money.
It sounds like you've invented lots of things, though, not just parts of GPS, but you kept on building on that. That's pretty impressive. So just as a side question, you make me think that a lot of engineers are kind of afraid of higher level physics. I'm curious, how technical do you have to be in this line of work? Do you have to know a lot about relativity and higher mathematics and all of this stuff?
No, it's not that complicated, quite frankly. I got onto, what physics I needed for this atomic oscillator. You don't have to be there's a lot of good people out there. First of all, you always have a physicist on staff for this kind of stuff, and then all you have to do is think straight a little bit and get the guy you have on staff to open his mind a little bit. And it's just not, for me, it's not that hard. But you also have to have a little bit of a knack for what you're trying to do. At Lion Tech, we were developing weapon systems, and the stuff I learned there. I mean, I was always the guy learning. Systems engineering, electronics is just my bag, and now I teach international economics at Pepperdine's grad school. So right now I'm more valuable there than I'm old now. So economics is a wonderful field, but to me, economics is systems engineering.
Oh, that's an interesting analogy. I hadn't thought about it that way, but it does make sense. Large systems that have to work together.
Yeah, global economics, my God, that's systems engineering if I ever heard it.
What kind of non-technical skills do you think engineers need to have today?
People skills. Engineers, the smarter they get, the harder they get along with. I've worked for two geniuses in my life, and I loved every minute of it because they were such pain in the butts. So
no
that
names,
would be the thing
guess.
that I noticed first.
Many thanks to my amazing guest, Hugo Fruehauf, electrical engineer and engineering CEO, as well as co-inventor of GPS. You can find out a whole lot more about the development of GPS and about Hugo's life and career at Hugo's website, hugofruehauf.com, linked in the show notes. This has been a co-production of the Engineering Word of the Day podcast and the K-12 Engineering Education podcast, made by yours truly under my studio, Pios Labs. Navigate yourself to more knowledge about engineering and engineering education by visiting the show websites engineeringwordoftheday.com and k12engineering.net. And hey, if you like what I do here, please consider supporting me at my Patreon. That link is at this episode's show notes or on the show websites. Once again, I'm Pius Wong. Thank you so much for listening.